Air power is engineered for destruction at distance. It is optimized to find, classify, and service targets through sensors, data links, and a kill chain that turns coordinates into effects. In that architecture, success is measurable. You can count sorties, bomb damage, radar tracks that disappear, and command nodes that go silent. The limitation is not a moral one and not a failure of technology. It is a design boundary. Air power can remove equipment and disrupt systems, but it does not, by itself, create control over terrain or people. It cannot occupy an intersection, hold a road, or physically block a unit from moving. It cannot compel compliance without a mechanism on the ground to enforce the new reality after the strike. That gap between destruction and control is where modern campaigns either end cleanly or drag on. This is the friction that surfaced in February 1991. For 38 days, coalition aircraft operated from a sterile standoff distance, raining fire from above with an assumption built into the planning model. Destroy enough hardware and the enemy's system collapses. But war does not terminate on a radar screen. A surrender cannot be accepted through a data link. Sensors can blink off, pilots go home, and the cockpit's distance collapses into the ground's persistence. The skies could be clean while the ground still belonged to someone else. Buried beneath sand and dispersed in protected positions, the Iraqi Republican Guard and coastal forces could endure punishment, reduce exposure, and wait for the campaign to shift into the domain where physics and probability favor mass, concealment, and proximity. From the adversary's perspective, the winning condition did not require defeating the United States Air Force in the air. It required surviving it long enough to force a transition. Saddam Hussein's wager was on a single variable: friction. If he could keep enough combat power intact and compel the coalition into a conventional fight where tanks meet tanks and infantry holds ground, the technological gap narrows and the timeline stretches. That is the structural logic of endurance under bombardment. It is not about winning the exchange. It is about denying the attacker a clean termination point. The United States military is built to avoid fair fights when it can. When a contested environment threatens to collapse the advantage of standoff destruction into a grinding ground contest, the system looks for a different lever, shaping the enemy's choices. In early 1991, that lever was not purely aerial. It required a parallel architecture that could change what the Iraqi command believed was about to happen, and force their forces to posture for the wrong problem. That is where the United States Navy became more than a supporting service. It became an instrument for creating operational control without immediately taking ground. The Navy's role here was not simply to shoot. It was to create conditions that made the coalition ground plan viable. While air power continued to attrit, the Navy engineered a physical trap tied to geography and perception. It fused elements that do not naturally belong together. World War II-era battleships, with their brute mechanical artillery, operating alongside early battlefield robotics that could extend vision over the horizon. The coastline was treated as an anvil. The intent was not to win the war from the sea, but to fix enemy attention and forces at the water's edge, so a separate maneuver, an armored hook through open desert, could land with maximum asymmetry. This is the beginning of the descent phase, where the campaign shifts from abstract dominance to the mechanics of forcing an opponent's disposition. The next step is to examine the environment that made this necessary: the shallow, constrained, adversary-favored waters along the Kuwaiti coast where the Navy had to operate, and why that battlespace imposed risks that could not be managed by technology alone. In open ocean, the geometry favors a blue water navy. Nuclear submarines extend detection and strike depth hundreds of miles forward. Carrier strike groups layer air defense, airborne early warning, electronic warfare, and long-range aviation into a moving perimeter that is difficult to penetrate symmetrically. In that environment, the United States Navy possesses near-infinite tactical depth. Engagements occur at distance. Detection precedes contact. The side with better ISR and longer-range weapons dictates tempo. The Iraqi command understood this asymmetry. They did not attempt to contest the fleet in blue water. Instead, they withdrew toward the green water along the Kuwaiti coastline, shallow, cluttered, geographically constrained. This was not retreat. It was environmental selection. In green water, the physics change. The seabed rises. Salinity and temperature layers shift. Acoustic propagation becomes unpredictable. Bottom clutter increases false returns. Radar horizons shorten because ships operate closer to land, and land itself becomes a source of reflection and masking. The deeper the fleet sails into littoral space, the more its sensors must discriminate between natural noise, civilian traffic, coastal structures, and military targets. The shoreline became a constructed kill sack. 11 Iraqi infantry divisions dug hardened fortifications into limestone caves and prepared defensive belts across likely landing beaches. Mobile HY-2, Silkworm anti-ship missile batteries, were concealed and operated in radar silence, waiting to ambush high-value targets that approached within range. But the objective was not to defeat the fleet ship for ship. It was to compress the battle space until American advantages were diluted by geography. From a systems perspective, littoral warfare forces trade-offs. Aegis radars are optimized for wide-area air defense, but land clutter complicates tracking. Concede the deep ocean. Fortify the approaches. Make entry costly enough that the attacker hesitates. This doctrine does not require decisive victory at sea. It requires imposing friction and raising the price of proximity. If the United States Navy must operate inside missile envelopes, within minefields, and under observation from concealed coastal positions, then each mile gained carries disproportionate risk. This is where technology alone is insufficient. Even with superior ISR, the littoral compresses decision time and multiplies ambiguity. A radar contact near shore might be a fishing vessel, a decoy, or a missile launch platform. A thermal signature could be a generator or a firing unit. Every misclassification carries strategic cost. The green water environment turns detection into a probabilistic exercise rather than a deterministic one. For the coalition, the operational question became binary. Attempt a real amphibious landing into a prepared defense under mine threat, or exploit the Iraqi expectation of that landing to shape their force disposition elsewhere. The environment made a direct assault expensive, but it also created an opportunity. If the Iraqi command believed the main effort would come from the sea, they would anchor divisions along the coast, reinforcing the very kill sack they had built. Before examining how that deception was engineered, one constraint dominates the picture. The weapon that most effectively equalized the exchange ratio in shallow water was not the missile battery on the cliff. It was the naval mine buried silently beneath the surface. The most efficient component of Iraq's coastal denial strategy was not visible from the horizon. It did not emit radar energy. It did not require a launch signature. It waited. The naval mine, particularly the Italian-made Manta bottom mine, transformed shallow water into a cost imposition engine. From an engineering standpoint, the Manta is designed for concealment and selectivity. It does not float on the surface like older contact mines. It rests on or buries itself in the silt of the seabed. Instead of detonating on physical contact alone, it uses acoustic and magnetic sensors to profile the signature of a passing hull. A large steel warship displaces water, generates a pressure wave, alters the local magnetic field, and produces a distinct acoustic pattern from its propulsion plant. The mine waits for the right combination. It is passive until the final moment. This creates a severe asymmetry. A Manta mine costs on the order of a few $1,000s. A Ticonderoga-class cruiser represents an investment measured in billions. If the mine detonates successfully, the exchange ratio is extreme. The objective is not necessarily to sink the ship outright. It is to mission kill it, to remove it from the fight, damage critical systems, and impose repair timelines that ripple through the campaign. More than 1,300 mines were seeded in the northern Persian Gulf. That density changes operational calculus. Mine countermeasures are slow by necessity. Ships must move deliberately. Helicopter-towed sleds, surface sweepers, and explosive ordnance teams clear lanes incrementally. Every cleared corridor consumes time. Time, in a joint campaign, is not neutral. It affects ground maneuver schedules, air tasking cycles, and political patience. The presence of mines forces a structural trade-off. If the Navy slows to clear extensively, it reduces risk, but sacrifices tempo and the credibility of imminent amphibious assault. If it accepts higher risk and pushes forward to generate operational pressure, it exposes high-value units to a cheap, persistent threat. Mines invert the traditional hierarchy of naval warfare. Instead of duels between capital ships, the dominant interaction becomes a probabilistic encounter with an unseen device on the seabed. This also constrains sensor dominance. Aegis radars and airborne early warning aircraft cannot detect a buried bottom mine. Thermal sights offer no advantage. Satellite imagery cannot easily distinguish a mine resting in silt. The problem becomes one of environmental management rather than target destruction. You are not hunting an emitting adversary, you are navigating a contaminated space. Strategically, the logic is coherent. Iraq did not need to defeat the fleet in open battle. It needed to make the fleet's proximity costly enough that amphibious operations appeared prohibitively risky. A credible mine threat magnifies the perceived danger of every coastal approach. Conduct a genuine amphibious assault into a mined, fortified coastline, or convert the enemy's fear of that assault into a strategic lever. The decision would not eliminate the mine threat. It would redefine how and why the fleet entered those waters. Given the mine density, fortified beaches, and compressed littoral battle space, a full-scale amphibious landing would have required extensive clearance, high exposure time, and acceptance of uncertain losses. The coalition did not select that option. Instead, it chose to weaponize the expectation of that option. The operation was codenamed Great Deception. The objective was precise: fix Iraqi divisions along the Kuwaiti coastline, convince their command structure that a major amphibious assault was imminent. If those units remained anchored in prepared defensive belts facing the sea, they would not reposition west to counter the Army's 7th Corps executing a wide armored maneuver through the desert. The Navy's task was not symbolic. It had to generate signals credible enough to survive Iraqi intelligence scrutiny. Deception at this scale cannot exist only in planning documents. It must produce physical signatures detectable by the adversary's sensors and reconnaissance networks. Battle groups were ordered to maneuver aggressively within visual and radar range of the coast. The battleships USS Missouri and USS Wisconsin initiated sustained naval gunfire bombardment. Navy SEAL teams conducted covert beach demolitions to simulate pre-assault clearing operations. Amphibious ready groups adjusted formations consistent with landing preparation. The acoustic footprint, radar emissions, and visible presence of large surface combatants created a data stream that Iraqi observers could interpret. From a systems perspective, this was coordinated signal generation. Each platform contributed to a composite narrative. Surface ships created radar returns and infrared signatures. Artillery impacts reinforced the impression of preparatory fires. Special operations activity suggested shaping of landing zones. The deception was effective because it aligned with Iraqi expectations. Given the geography of Kuwait, an amphibious thrust toward Kuwait City was plausible. The Navy exploited that plausibility. However, credibility required proximity. To make the threat convincing, ships had to operate inside the engagement envelope of coastal defenses and within mine-contaminated waters. A deception that remains over the horizon lacks weight. A deception that closes distance carries risk. The fleet had to accept exposure to mines and anti-ship missiles in order to maintain the illusion of imminent assault. This trade-off illustrates institutional decision-making under constraint. Protecting capital ships is a priority, but so is enabling the ground campaign. If keeping divisions fixed along the coast reduces resistance against the main armored maneuver, the risk to ships may be operationally justified. The deception, therefore, was not an auxiliary effort. It was integral to the joint plan. Iraqi command structures responded as anticipated. Divisions remained dug in along the shoreline, oriented seaward. Defensive preparations intensified rather than redistributed. Their attention remained fixed on the horizon, while hundreds of miles to the west, armored formations repositioned for the eventual ground offensive. But signal generation in a mined littoral does not occur without consequence. By pushing forward to sustain the illusion, the fleet entered the very hazard field that Iraqi planners had constructed. On February 18, 1991, the cost of maintaining credibility materialized. On February 18, 1991, the mine threat shifted from abstraction to impact. The amphibious assault ship USS Tripoli struck a contact mine while operating in the northern Persian Gulf. The explosion tore a hole approximately 16 by 20 feet in her starboard hull. Minutes later, the Aegis cruiser USS Princeton triggered a bottom influence mine. The detonation occurred beneath the hull, creating a rapidly expanding gas bubble. As the bubble rose and collapsed, it lifted the stern and then dropped it. The structural effect is known as whiplash. The shock buckled the keel, cracked sections of the aluminum superstructure, and severed cooling lines feeding the SPY-1 radar system. In seconds, a billion-dollar combatant was degraded. This sequence illustrates the distinction between sinking a ship and mission-killing it. Neither vessel was lost. Both, however, experienced system-level disruption. Electrical circuits tripped, fire mains ruptured, combat systems went offline. The design assumption embedded in U.S. naval architecture is not invulnerability, but recoverability. Warships are compartmentalized to contain flooding and preserve buoyancy. Critical systems are distributed and redundant where possible. Yet those design features are inert without execution. The decisive system in this moment was damage control. On both ships, crews implemented zebra protocols, closing watertight doors, isolating compartments, reinforcing bulkheads, and rerouting power and cooling lines. Damage control is procedural engineering. It relies on training cycles, standardized checklists, and drills repeated in peacetime. Panic is treated as a variable to be minimized through repetition. The objective is not rapid perfection, it is stabilization. The Princeton restored partial radar coverage within approximately 2 hours. Tripoli remained on station to support mine-clearing operations despite structural damage. From a purely protective standpoint, withdrawal would have reduced exposure. From an operational standpoint, departure would have signaled vulnerability and potentially weakened the deception. The decision to remain in position was a calculated acceptance of continued risk in exchange for preserving strategic effect. This is a key trade-off in naval operations. Capital ships represent concentrated capability. Losing one has operational and political consequences. However, abandoning a position prematurely can undermine joint synchronization. The deception required visible presence. The ground maneuver in the west required Iraqi divisions to remain oriented toward the sea. Holding station after being struck reinforced the illusion of imminent amphibious assault. The mine incidents also reinforced an institutional lesson. A2/AD threats do not need to destroy platforms outright to influence outcomes. Temporary degradation can shift timelines and alter decision cycles. Resilience, therefore, becomes as important as firepower. A navy operating in contested littoral space must assume it will be hit at some point. The differentiator is whether it can absorb shock and continue contributing to the mission. With the deception intact and the fleet still present inside the contested zone, the operational trap held. Iraqi forces remained fixed along the coast, while approximately 250,000 coalition troops maneuvered through the desert to the west. The architecture was now set, but remaining inside the kill sack required more than endurance. It required a synchronized structure capable of surviving missile attack, projecting power ashore, and sustaining pressure simultaneously. Operating inside the littoral kill sack required the fleet to function as an integrated architecture rather than a collection of individual hulls. Survival, projection, and destruction had to occur simultaneously. If any one function failed, the others would collapse under cumulative risk. The system can be understood as a three-stroke engine. First, survive incoming threats. Second, provide responsive support to forces ashore. Third, apply heavy kinetic pressure against fixed defenses. The first stroke is survival. Before projecting power inland, ships must remain afloat and combat capable under missile and mine threat. The nightmare scenario for the U.S. Navy has long been saturation attack, multiple anti-ship missiles launched from concealed coastal batteries. On February 25, 1991, that risk materialized. Iraqi forces on the Al-Fa Peninsula launched two HY-2 Silkworm missiles at the battleship USS Missouri operating near shore. The Silkworm carried a large warhead and approached at low altitude, skimming the sea surface to reduce radar detection time. In littoral geometry, reaction windows shrink. When the vampire call went out, the fleet's defensive architecture activated. Missouri deployed chaff to create false radar returns and seduce the missile's seeker. One missile diverted and impacted the water. The second continued inbound. The British destroyer HMS Gloucester, operating within the same defensive envelope, detected the threat and launched Sea Dart missiles. Using semi-active radar guidance, Gloucester illuminated the target until intercept. The Silkworm was destroyed seconds before impact. This engagement was not the product of a single platform. It was the outcome of layered sensors, allied interoperability, and compressed decision cycles. From a systems perspective, point defense in 1991 was reactive. Semi-active missiles required continuous radar illumination. Human operators confirmed tracks and authorized engagements. The architecture functioned, but it relied on rapid coordination and favorable geometry. The event demonstrated both capability and limitation. As threats increase in speed and complexity, reaction-based defense approaches physical constraints. The second stroke is projection, specifically providing close air support to Marines advancing toward Kuwait City. Land-based aircraft operating from Saudi Arabia faced long transit times. Turnaround cycles extended sortie intervals. The amphibious assault ships, often referred to as the Gator Navy, were reconfigured to operate AV-8B Harrier II aircraft. The Harrier's vertical, or short takeoff and landing capability, allowed it to operate from smaller decks positioned close to shore. The Harrier was not optimized for speed or payload compared to conventional carrier aircraft. Its advantage was proximity. From ships positioned offshore, Harriers could launch, engage, and return within roughly 20-minute cycles. In systems terms, this reduced latency between request and effect. Marines encountering resistance could receive air support quickly. The trade-off was vulnerability and limited endurance. The aircraft relied heavily on pilot visual acquisition and operated within reach of ground fire. It was a tactical solution shaped by geographic constraint. The third stroke is heavy kinetic pressure against fixed coastal defenses. While Harriers provided responsive support, battleships like USS Missouri and USS Wisconsin delivered sustained naval gunfire. Their 16-inch guns fired 2,700-pound shells at targets up to 20 miles inland. These were unguided ballistic projectiles governed by trajectory mathematics rather than onboard intelligence. The constraint was observation. Gunners could not directly see impacts beyond the horizon. To bridge that gap, the Navy employed the RQ-2 Pioneer unmanned aerial vehicle. Primitive by modern standards, the Pioneer transmitted live video back to the ship, enabling spotters to adjust fire. This integration of mechanical artillery and remote sensing formed a temporary system of systems. It combined massive kinetic energy with real-time correction. On Failaka Island, Iraqi soldiers reportedly surrendered after observing the UAV overhead, recognizing that artillery fire would follow. The psychological effect derived from integration, not from any single component. These three strokes, defense, responsive air support, and heavy bombardment, operated concurrently. Each imposed trade-offs in risk, range, and resource allocation. Together, they allowed the fleet to remain inside contested littoral waters while sustaining operational pressure. The architecture held long enough for the ground maneuver in the west to unfold, but survival under missile threat in 1991 relied on semi-active systems and human-mediated engagement loops. As missile technology evolved, faster speeds, decoys, electronic countermeasures, the margin for human reaction narrowed further. The next evolution would require shifting the trigger itself from biological response to machine speed automation. The Silkworm engagement in February 1991 is often remembered as a successful intercept. From a system standpoint, it was a stress test of the fleet's defensive architecture under real conditions. The incoming HY-2 missiles forced the task group to execute a layered response: electronic countermeasures, decoys, radar tracking, command authorization, and missile launch. Each step consumed seconds. In littoral waters, seconds define survival margins. The Sea Dart intercept by HMS Gloucester was historically significant. It marked the first time a warship shot down an incoming anti-ship missile in combat. But the technical reality was complex. Sea Dart was a semi-active system. It required continuous radar illumination of the target until intercept. That means the ship's fire control radar had to maintain lock while the missile flew. The engagement envelope was finite. If sea state, land clutter, or jamming disrupted tracking, the intercept probability would decline. This exposes the trade-off inherent in 1991-era point defense. The architecture was effective against subsonic threats approaching at predictable altitudes. It was less suited for saturation attacks or higher-speed missiles. Reaction time depends on detection range. Detection range depends on radar horizon and signal clarity. In littoral geometry, both are constrained. The event also demonstrated the importance of interoperability. Gloucester's sensors and weapons operated within a coalition defensive framework. Data sharing and rules of engagement were aligned sufficiently to permit cross-platform defense. A single ship did not save another in isolation. The network absorbed and redistributed the threat. That cooperative layer is institutional, not technological alone. It requires standardized procedures, communication protocols, and prior integration exercises. However, even with successful interception, the engagement highlighted a structural vulnerability. Defensive systems were largely reactive. The fleet waited for launch, detected inbound tracks, then responded. As missile technology advanced, introducing sea-skimming profiles, electronic countermeasures, and eventually supersonic and ballistic trajectories, the timeline between detection and impact compressed further. At Mach 2, a missile covers roughly a mile every 3 seconds. At higher speeds, human verification becomes a bottleneck. This is where the concept of removing the human from the immediate firing loop begins to emerge. In 1991, operators in combat information centers processed radar returns, confirmed hostile intent, and authorized engagement. The Aegis Combat System and AN/SPY-1 radar provided automated tracking and fire control support, but human oversight remained central. The system could track dozens of targets, yet decision authority often remained biological. The limitation is physiological. Voice commands over radio consume time. Cognitive processing under stress consumes time. Mechanical radar rotation imposes refresh intervals. When threat velocity increases, these delays become structural weaknesses. The Navy's long-term response would involve enhancing automation, improving radar discrimination, and integrating missiles capable of active terminal guidance without continuous ship illumination. The Silkworm incident, therefore, represents a transitional moment. It validated layered defense while exposing the narrow margin under which it operated. Survival inside an A2/AD envelope demanded not just bravery or discipline, but architectural evolution. To remain viable in future contested environments, the fleet would need sensors that see farther and more clearly, and interceptors that act with greater autonomy. That evolution does not occur in isolation from other mission demands. While defensive systems adapt to faster missiles, the fleet must also project power inland with greater precision and efficiency. The shift from unguided naval gunfire supported by external spotters to weapons carrying onboard intelligence reflects the same institutional pressure. Reduce latency, reduce dependency on vulnerable links, and compress the kill chain. While missile defense tested the fleet's survivability, the campaign along the Kuwaiti coast exposed another constraint: distance. The main coalition air bases were located deep in Saudi Arabia. For fast jets operating from those airfields, transit time to targets near Kuwait City consumed fuel, limited loiter, and stretched turnaround cycles. In close air support, latency matters. A request delayed is in effect denied. The amphibious assault ships, USS Tarawa, USS Nassau, and others, were originally designed to transport and land Marines. In Desert Storm, they were reconfigured to operate AV-8B Harrier II aircraft at scale. This adaptation reflects institutional flexibility under operational pressure. Rather than relying solely on large deck carriers positioned farther offshore, the Navy created localized air nodes closer to the battlespace. The Harrier is an engineering compromise. Its vertical, or short takeoff and landing capability, relies on vectored thrust nozzles. That configuration sacrifices maximum speed and payload relative to conventional fixed-wing fighters. Range is limited. Endurance is modest. However, proximity compensates for those deficits. Positioned just off the coast, Harriers could launch, deliver ordnance, and return within roughly 20-minute cycles. That compressed sortie loop provided Marines with responsive aerial support. From a systems perspective, this is a trade-off between performance envelope and temporal advantage. A faster aircraft operating from a distant base may carry more weapons but arrive less frequently. A VTOL aircraft operating nearby delivers fewer munitions per sortie but appears overhead more often. In close combat, frequency can outweigh magnitude. The Gator Navy functioned as a floating forward airfield optimized for cycle time rather than peak output. There were constraints. The Harrier relied heavily on pilot visual acquisition and forward air controllers for target identification. In a contested environment with small arms and shoulder-fired threats, operating at lower altitudes increased vulnerability. Maintenance demands on amphibious decks were significant. These ships were not originally built as high-tempo strike platforms. Yet the configuration matched the operational requirement: immediate support to Marines advancing toward Kuwait City. This arrangement also reduced dependency on fixed land infrastructure. Amphibious assault ships could reposition along the coastline, adjusting geometry relative to ground units. Flexibility of basing translated into flexibility of support. It did not eliminate risk, but it redistributed it into a more controllable domain. Desert Storm revealed the value of proximity as a design parameter. In later decades, this logic would expand into the concept of the Lightning Carrier, with America-class amphibious assault ships optimized to operate F-35B aircraft. Unlike the Harrier, the F-35B integrates stealth, advanced sensors, and data fusion. The shift reflects an institutional move from simple responsive firepower toward distributed sensor networks at sea. In 1991, the ship served primarily as a transport and improvised strike deck. In later iterations, it becomes a floating node in a broader ISR and command architecture. But in February 1991, the immediate requirement was practical: reduce response time and maintain pressure on coastal defenses. Harriers filled that gap. Their sorties complemented naval gunfire from battleships positioned offshore. Together, they applied sustained kinetic stress against Iraqi positions. The next layer of that stress came from platforms many considered obsolete. Mechanical artillery designed in the 1930s was about to merge with early unmanned aviation, forming a temporary bridge between eras. The battleships USS Missouri and USS Wisconsin represented an earlier design philosophy: concentrated armor, massive guns, and mechanical reliability. Their 16-inch/50 caliber guns fired 2,700-pound shells at supersonic velocity. Each projectile followed a ballistic trajectory governed by Newtonian physics. Once fired, it could not adjust course. There was no onboard guidance. The system's strength was raw kinetic energy. Its limitation was observation and correction. In coastal Kuwait, that limitation was structural. The curvature of the Earth and terrain masking prevented direct visual confirmation of impacts beyond the horizon. Without accurate spotting, heavy naval gunfire risks inefficiency. The Navy addressed this by integrating the RQ-2 Pioneer unmanned aerial vehicle. By modern standards, Pioneer was rudimentary. It was loud, slow, and recovered via net on the ship's deck. Its video feed was grainy, yet it extended the ship's line of sight inland. This created a functional system of systems. The battleship provided energy. The UAV provided feedback. Spotters adjusted firing solutions in near real time based on transmitted imagery. The integration bridged decades of technological evolution. Mechanical artillery from the mid-20th century was effectively paired with first-generation battlefield robotics. On Failaka Island, Iraqi troops reportedly surrendered after observing the Pioneer overhead, aware that naval gunfire would follow. The episode illustrates how surveillance alters behavior even before impact. However, from an engineering standpoint, the architecture remained heavy and linear. It required multiple synchronized components: the ship, the UAV, the communication link, and trained spotters. If any link failed, accuracy degraded. This dependency reveals the trade-off inherent in the system. Large-caliber naval guns deliver sustained fire without the cost of missiles per shot, but they demand significant platform size and logistical support. Ammunition storage, recoil absorption, and crew requirements are substantial. Moreover, effectiveness relies on external targeting. The gun itself does not know where to go beyond programmed coordinates. Following Desert Storm, the battleships were retired. The decision reflected institutional reassessment rather than obsolescence in isolation. Maintaining large gun platforms for limited-range bombardment was resource-intensive. As guided munitions matured, precision could be achieved without deploying a 45,000-ton ship into contested littoral waters. The subsequent evolution inverted the architecture. Instead of pairing a dumb projectile with an external observer, intelligence migrated into the munition itself. Systems like the AGM-158C long-range anti-ship missile embody this shift. Unlike a ballistic shell, LRASM is aerodynamic and stealthy. It carries onboard sensors and algorithms capable of identifying and selecting targets based on electromagnetic emissions and environmental cues. It does not rely exclusively on GPS or continuous data link guidance. The weapon processes information internally during flight. This reduces dependence on vulnerable external links and shortens the kill chain. In 1991, targeting required coordination between multiple platforms. In later systems, decision-making compresses within the weapon. The trade-off shifts from platform mass to software complexity and sensor fidelity. Instead of sustaining heavy artillery ships, the Navy invests in distributed launch platforms capable of deploying intelligent munitions from safer distances. The transition from battleship gunfire guided by UAV to autonomous missile systems reflects a broader institutional pattern. Minimize latency, reduce exposure, and embed adaptability within each component. Yet embedding intelligence inside weapons introduces new dependencies: software integrity, data validation, and resilience against electronic warfare. As firepower becomes more discriminating and autonomous, the final layer of survivability lies not only in the weapon, but in the sensor architecture that detects and classifies threats in the first place. In saturated airspace, discrimination becomes more valuable than volume. In the northern Persian Gulf of 1991, the final constraint was not simply seeing the enemy, it was processing information fast enough to act before impact. At long range, the fleet relied on the E-2C Hawkeye for airborne early warning. Radar operators tracked contacts on green displays and transmitted bearings and ranges over voice circuits. That structure functioned when timelines allowed minutes for evaluation. In terminal phases measured in seconds, voice becomes latency. The Aegis Combat System, deployed on Ticonderoga-class cruisers like USS Princeton, was designed to compress that timeline. Its AN/SPY-1 radar did not rotate mechanically. It used passive electronically scanned array technology to steer beams at the speed of light. Instead of sweeping periodically, it stared continuously, refreshing tracks rapidly, and maintaining persistent awareness within its sector. In auto special mode, Aegis could track scores of targets, evaluate trajectories, and generate firing solutions in milliseconds. This marked a structural shift. The system was no longer just a sensor feeding human decision-makers. It was a digital reflex integrated with missile launchers. However, in 1991, human oversight remained embedded in the loop. Operators confirmed engagement logic and retained authority over weapon release in many scenarios. The architecture was advanced for its era, yet optimized primarily against subsonic, relatively unsophisticated threats. As missile technology evolved, introducing sea-skimming profiles, decoys, electronic jamming, and later ballistic trajectories, the requirement shifted from volume engagement to discrimination. Modern anti-ship ballistic missiles approach at high Mach numbers from exo-atmospheric arcs. Reaction windows compress further. Under those conditions, semi-active guidance and prolonged radar illumination become limiting factors. The Navy's subsequent response included missiles such as the SM-6, equipped with active radar seekers derived from air-to-air systems. Unlike earlier interceptors, these missiles do not require continuous ship-based illumination in the terminal phase. They carry their own sensing capability. This allows engagement over the horizon and increases flexibility against maneuvering or electronically contested targets. The shift reflects an institutional recognition that autonomy within the interceptor reduces strain on centralized control. Parallel to this, radar evolution moved from SPY-1's earlier architecture towards systems like SPY-6, incorporating gallium nitride technology. Increased sensitivity and resolution enable finer discrimination, distinguishing decoys from warheads, identifying smaller cross-section objects, and tracking multiple threat vectors simultaneously. The emphasis is no longer solely on detecting a blip, but on classifying it accurately under clutter and countermeasures. This progression underscores a consistent theme across Desert Storm and beyond. Whether through damage control procedures, Harrier sortie cycles, UAV-assisted naval gunfire, or Aegis automation, the Navy incrementally reduced latency and redistributed intelligence across the system. Human operators remain central, but their role shifts from direct trigger pullers towards supervisors of automated processes. When the ground campaign concluded after 100 hours, the operational outcome was visible in destroyed equipment and captured territory. The underlying mechanism, however, was architectural. Air power dismantled surveillance and command nodes. Naval deception fixed enemy forces along the coast. Missile defense preserved fleet survivability. Proximity-based aviation reduced support latency. Heavy bombardment applied sustained pressure. Automated combat systems compressed defensive timelines. The campaign was not a sequence of isolated engagements. It functioned as a continuous network of interlocking systems, each compensating for the other's limitations. The blueprint visible in 1991 was transitional. It revealed both capability and constraint. As adversaries acquire more advanced ISR, faster missiles, and denser electronic warfare environments, the central question becomes structural. Can the mechanisms that produced credible deception and layered defense in 1991 operate with the same effect against a sensor-saturated opponent? That question extends beyond individual platforms. It concerns how signals are generated, how decisions are automated, and how resilience is engineered into contested environments where detection is reciprocal and latency is minimal.